All right, welcome to today's lesson on factoring or graphs of factored cubics. And this is where our knowledge starts to take a bit of a turn towards general general situations rather than specific examples. All right, so bear with me. We've previously looked at graphs of cubics that look like this with an a value x minus h cubed plus k, and you might remember that they were essentially like this. All right, so they'd start from down here and they'd go up. They'd have this section, if you remember what it was called a point of inflection. All right, a point of inflection, and then they kept rising. Okay, if you made the cubic negative, it would just reflect it and it would look like this, the opposite direction, right? But it still had this point of inflection here in the center. Okay, so it would start going down, level off, and then keep going down. So this sort of introduces us to our cubic factors. All right, so we've got from our journey from in algebra has been looking at straight lines, which are graphed like this. The brackets are not necessary, but I'm putting them in there for a reason. So straight lines, that this could be there. All right, you notice that it hits the x-axis exactly once there. All right, and conveniently, that is the highest power in this problem. All right, the next thing we looked at were quadratics, which could have been graphed like this. All right, the highest power is 2, and this had two factors, but instead of going through the x-axis twice, which was possible, this one touched at this point here. All right, touched at that point there. If we'd graphed it as two different factors, it would have gone through the x-axis at two different points. All right, so it would have gone through here and here, like so. All right, so quadratics could have two intercepts possible. Linear equations, only one possible intercept. Cubics, previously we'd only seen this point of inflection, which is only one intercept. But what I want to talk about today is actually the behavior. So when you see a factor that is repeated 3 times, it automatically means it has this point of inflection in it somewhere. But it's not the only graph possible for a cubic. So what happens if you had a cubic that was, say, something like this, where y equals x minus 1, x plus 1, x plus 2. So there are 3 different factors here. All right, so this graph is going to look a bit different. Notice that it doesn't have a quadratic factor, which means it has a turning point on the x-axis. It doesn't have a cubic factor, which would have meant a point of inflection. It has got 3 linear factors, as they're called. All right, and what these factors mean is that at each point, the graph cuts through the x-axis. So to calculate this, you would use your null factor law as you've practiced at doing, and you would say 0 equals x minus 1, x plus 1, or x plus 2. If this is the case, then either one or all of those is equal to 0. So there are 3 possibilities. It could be x equals 1, -1, or -2. So if we put those onto our Cartesian plane, you'll have that one there and those out there. Then you've got to fill in the blanks. You've got to know what happens between them. So to find the y-intercept, which is another point we can use, we'll set x equal to 0. So it's going to be y equals 0 minus 1, 0 plus 1, 0 plus 2, which is going to give us minus 1, 1, 2, which is going to give us minus 2. So the fourth point really is down here. So we know now that between these two intercepts, this has to be the path it takes. That means that between these two intercepts it has to go there. And then because there's no other intercepts, it just has to continue on like that. So you can see here that this cubic function has got 3 intercepts and a y-intercept, and comes from below, loops around, goes back again, and then finishes going up. So compare that to this black one up here. Notice that it started out in the bottom left area, came up, leveled off, and then kept rising. This is a positive cubic. If it starts down here and finishes up here, it's positive. And notice that in this equation, there was no negative out the front of the brackets. If there had been a negative, it would have looked the mirrored version of this red graph. All right, so it would have started up here, come down there, up, back up, through, and then kept going down and becoming more negative. All right, there are other ways of calculating this using things called sign diagrams. You might remember those. All right, but the process I just showed you is probably the most straightforward. First of all, identify the three x-intercepts, plot them, identify the y-intercept, and use that to help you map out the direction that the path must take. So for instance, if the y-intercept is between two x-intercepts, then it must go through from each x-intercept through the y and then back to, okay? There's no, what I just graphed, there's no guarantee that the turning point is just there, all right? It could have gone straight down there and then looped rather sharply around if that was the nice path the parabola took, all right? So if the y-intercept is not halfway between the two x-intercepts, then there's no guarantee, all right? So what we're interested in doing here is just graphing or sketching the intercepts. We're not interested in giving coordinates of turning points, okay? Because there's ways of doing that which are actually quite easy. First and foremost, this year we'll use our CAS calculators to do it. So when you've sketched on your CAS, you just go analyze and find the turning point. True. Cubics can also be in factored form, and there's different numbers of factors up to a maximum of 3 that cubics can have because of the highest power of 3. All right, 3 linear factors means that it touches the x or cuts through the x-axis 3 distinct times. All right, so in this question, we've been asked to sketch the graph of px equals x cubed plus 2x squared minus 5x minus 6. Now, you might remember that to sketch, we need to know x-intercepts, y-intercepts, and any other important information on the graph. I'm trying to get this Cartesian plane nice and straight, but I haven't been able to do it. So one point that I can put on there straight away is the y-intercept at minus 6. Let's put it down here. All right. The other information that I can gather from this graph is that it's a positive cubic because there's no negative sitting out here, which means that it starts somewhere here and finishes up here. Everything else I'm going to have to calculate. This is the only pieces of information I can read off this cubic. All right, so let's get to it. To find the x-intercepts, I'm going to have to factorize, which means using my factorizing or long division skills. So I'm going to start with factor theorem. Factors of minus 6 are minus 6 and 1, 6 and minus 1, 2 and 3, 2 and minus 3, or minus 2 and 3. So let's just start plugging in factors of that could work. So I'm going to start with the easy ones. P at 1 is 1 cubed plus 2, 1 squared minus 5, 1 minus 6, which is 1 plus 2 minus 5 minus 6. I can see that that's not going to work. It doesn't equal 0, so P at 1 is not a factor. Let's try P at minus 1. Minus 1 cubed plus minus 1 squared minus 5 times minus 1 minus 6, which is equal to minus 1 plus 2. Minus 1 squared is 1 times 2 is 2, plus 5 minus 6. I can see here that's going to make 7, and then the remainders are going to make 7 also, so 0 equals 0. So minus 1 is a factor. So that's the first point I can put on here. Then I'm going to turn to my division, and I'm going to calculate what the remainder or the quotient is when I divide this by the factor, and I'm going to use synthetic division because I can't be bothered doing long division. So we'll write out our factor there. Oops, wrong spot. There, we'll put our coefficients in, which are 1, 2, minus 5, and minus 6. Drop it down, multiply it up to there. That gives us add down gives us 1, multiply it up to there, add down, that gives us minus 6, multiply it up to there, add down, it gives us 0. So these are now the coefficients of my new polynomial with one power less, so it's x squared plus x minus 6. If I can factorize that, we'll have all our factors. So these are positive 3 and minus 2. Chuck the extra factor on the end that we already know, and there are our factors. So sketching those factors on the graph, we've got x equals minus 1, which we already knew, x equals positive 2, which is out here, and x equals minus 3, which we'll say is here. So now we've got the required information. We knew that it was a positive, which means it starts from here and ends up there. We know that it goes through this y-intercept here, like this. We know that it comes back down somewhere and goes back down there. All right, so this is the information we need. You can see here that the graph is pretty shoddy. All right, it should reach a peak midway between these 2 points here, like that. That's a bit better, not much. And you can see this is an example of what I was saying in the first case. This y-intercept is not midway between the two x-intercepts, so it's going to come down here, but the turning point is going to be further out like that. All right, so it has to go further down before it turns around. So you can see that this is why we're not actually interested in finding the locations of the turning point, because there's it's actually quite complex to do. Like, you can try it if you want to. You can just plug numbers in until you find out where it is, but we'll get to some better ways of doing it later on. I don't want you to develop bad habits of thinking that your graphs of cubics have to be super exact. What I'm really interested in is the behavior, so whether it is a negative or a positive, where the x-intercepts are, and then where the turning points are. All right, so sorry, not the turning points, where it turns, between which intercepts it turns around. That's better. All right, so to recap, you might notice that these three factors are all different, which means they're called linear factors, and that shows you where the cubic cuts through the x-axis at. So it cuts through at 1, cuts through at 2, minus 1, and minus 3. Skipping. It's also possible. All right, so in this one we've been asked to sketch the graph of this cubic here. Now, it doesn't look like a cubic because it's been factorized partially first, but if you were to expand out the brackets, you would have something like this, all right, which you can see as a cubic has the highest power of 3, all right, but it has this quadratic factor, which we know is the same as x plus 0 squared. So another way of writing this would have looked like that, and if you'd seen it in fully expanded form, it would have looked like this. All right, so this is where our knowledge of repeated factors come in. So we should know that a quadratic means a turning point on the x-axis, and this h value tells us where. So there's a turning point on the x-axis there. There's also a factor of positive 1, which is here. We notice that at the start here there's no positive or minus, which means it's a positive, which also means that it starts somewhere in this quadrant and finishes somewhere up here. We know that it has to touch the x-axis at x equals 0. There's a turning point, so it's going to look something like this. So it's going to start down here, come up, somewhere in between these two intercepts it's going to turn around again, and then go up and continue going up. All right, so quick sketches of cubics, when you know the factors, start becoming really quite easy, because you don't have to know the exact values of the turning points if you can't find them. You just have to understand what the factors are telling you. So what you need to remember is that linear factors cut the x-axis, quadratic factors touch the x-axis, and cubic factors are points of inflection which cut as well. All right, knowing that, you're ready to go into all sorts of other higher powered factors and use your knowledge to do really quick sketches of them. To touch the x-axis once and cut through it once using a quadratic factor still has 3 factors. What you notice here is that the power on this linear factor is 1, 2 plus 1 is 3, and so we've got our highest power of 3. All right, so a quadratic factor is a touch, a linear factor is a cut. The last thing that's possible is a cubic that has this feature. All right, so let's have a look at what the feature is. So we'll do a quick Cartesian plane here. We'll interpret the information that's been given to us. It's a negative, which means it starts up here and ends down here. It goes through at +1, which is, let's say it's here. And this is the other factor. It's a quadratic factor. So I'm looking straight away to try and factorize it. I'm thinking 5 and 1, and because they're both positive, they have to be the same, which means I'm not going to be able to factorize this by sight. So I'm going to turn to my completing the square. But before I do, I might just evaluate the discriminant for this quadratic. So it's going to be 16 minus 20. And you can see here that the discriminant is negative, therefore not factorized, not factorizable, and therefore no intercepts. So this is a quadratic which doesn't go through the x-axis, which means that this one we've already graphed is the only one. All right, so your cubic might look something like this. Okay, where it has a turning point that is above the x-axis and therefore doesn't touch. The only other piece of information we need to find out is the y-intercept to work out where it goes through the the y-axis. So we're going to set x equal to 0, y equals minus 1 times 5, which is equal to 5. So this point here is 5. All right. So knowing that, you can't really accurately graph that, all right, unless if you want to sub in some x values to find out what the y values are, and that will give you a much better idea as to the path that this cubic takes. All right, but you don't need to do that because you've just been asked to sketch it using the information or the skills that you know. All right, so if we wanted to take forever, we could do a table of values for this and then plot each and every one of them. But you can see here that you need quite a few of them to get a really accurate picture of this graph. Far better thing to do is to use your CAS calculator to analyze for the max and the min to find out where the turning points are, and then plot those on your sketch. So if I was to enter this, analyze the graph, find out what it is, and then label it on my sketch, that's a far better, more efficient way of doing things. All right, so to recap, it's also possible to have only one x-intercept and the other factor is either not factorizable or doesn't touch the x-axis. All right, so your choices are it has 3 intercepts, it has 2 intercepts, or it has 1 intercept. You might notice that due to the behavior of this, it's not possible, unlike quadratics, for it to have 0 intercepts, all right, because it has to start in opposite quadrants, diagonally opposite quadrants, start and end, which means it's always going through the x-axis at least once. All right, so lock that away for your brain future usage.